Hi everybody, I'm Tuncel. Welcome to our presentation on variable piezoelectric energy harvesting using human motion. The following video highlights our motivation.
What if you didn't need a battery to track your activity? What if you could wear technology that is powered by activity? How about not having to worry about charging? Thanks to novel sensing technologies and low-power design techniques, state-of-the-art wearable devices can achieve ultra-low energy consumption. The combined benefits of low power consumption and edge processing allow these devices to be powered through energy harvesting. Flexible light and motion energy harvesters can replace batteries, hence making the design less bulky and removing the recharge requirements. Come join us. Focus on your health, not the batteries.
I will start with the major innovations and contributions of this work. First, we focus on energy harvesting from low-frequency, large-bending human motion using flexible piezoelectric transducers. In contrast to our approach, existing approaches typically use high-frequency vibration as the motion, and they use brittle and inflexible piezoelectric materials. Second, we develop a mathematical model that relates the large joint bending motion to generated electrical energy. Now, this model is useful to predict the energy harvesting potential from a wide array of different motions, such as walking, running, or cycling. There is no modeling study in the literature that target large bending human joint motions. Third, we design and fabricate an experimental setup to demonstrate the energy harvesting potential from the same low-frequency, large bending human motion. Through this setup, we collect important experimental data from different MFC piezoelectric patches and validate our mathematical model. Most existing work placed the piezoelectric elements directly on human subjects, which do not yield repeatable and reliable results. Also, previous work do not combine the experiments and models together. I'll introduce the setup in more detail now. First, we have the frame that mimics the joint, and on this frame we place the flexible piezoelectric element and clamp it from one end. The other end is free and is coupled to the frame with the help of a transparent cover that is placed on the upper leg. The piezoelectric element slides under this cover. The frame is actuated by a Dynamixel AX12A servo motor, and the motor is controlled through an open CM motor controller. The two terminals of the patch is terminated by a variable resistance box, and finally we record the generated voltage with a NI DAC at 1 kilosamples per second. Here's a short clip of the system in action. Here we charge 100 microfarads of capacitance, and the horizontal axis is time in seconds. The following results have been obtained from the MFC 8528 piezoelectric module. Starting with the voltage, we see that it is 10 volts peak to peak. We can also see that the output waveform is distorted and is no longer a pure sinusoid. Next, we illustrate the generated power for different bending motions. For the power results, I'll just focus on the 60° 1 Hz motion, as it is the closest among these four to human walking in the interest of time. With this motion, the system can generate up to 10 microwatts of power. In summary, we presented an experimental exploration of energy harvesting from joint bending. To conclude the presentation, our model predicts that we can harvest 7.8 microjoules per step when walking. This is sufficient to power many low-power designs. As a reference, 10,000 steps per day over a month is equivalent to 0.5 mAh battery. For more details, please refer to our 20-minute presentation on the conference webpage. Thank you for listening.